So hello everyone and welcome to this next lecture. So in the previous lecture we had analyzed the performance of the buck converter. So in this next lecture, or rather the last lecture, where we'll be concluding the buck converter series, and I'll be starting in the next lecture with the boost converter. Here we will talk about some other aspects of the control. At least I won't go into the details of control, but I'll tell you about how it can be achieved. And finally we'll wind up this lecture. So before I start off with this lecture, just in case you are interested in this kind of a topic and you would like to know more about simulating power electronics using Python Power Electronics, I have a full-length course on Udemy, which is the online website for online courses, and in this you can actually go through the entire process of how you simulate. It tells you about how you can install the simulator, a little bit of basic theory about circuits, and so on and so forth. So in case you're interested but you find these lecture series to be a little too light, you could consider enrolling for this course. Now coming back to this lecture series, what we're going to do in this is we are going to alter the modulation signal. So let me go back to my control file. So this is the control file that we have, where we are generating the switching pulses. In the switching pulses we have a constant modulation signal of 0.3, right? And that's perfectly okay for now, because I wanted to show you how the buck converter works and how the switching signals is generated. But in reality, when you are using a buck converter, you would need to regulate the output voltage, which means you don't just want the output voltage to be some random value, you want it to be regulated to something. For example, you have a requirement of a 9-volt regulated output voltage, in which case if your input voltage were to fluctuate, you would still want that output voltage to be regulated at 9 volts, which means the modulation signal will have to change, or rather the duty ratio would have to change. So therefore, what we will do is, let's go back to the simulation and we will add another control file. So let's go back to edit control, and here let's add a file. So for that, let's create a file. So in this same folder, which is the buck converter folder, I'm going to add another file, which is a new file, and I'm going to call this what will I call this? Let me call this open loop control. The reason I'm calling it open loop control is because I'm not actually implementing a rigorous control. I'm just going to do an open loop control just to give you an idea what it is. So let's add this file. Choose the file. We are in the buck converter. It's important to see that you are in the buck converter directory. We go to our file. Where is it? Open loop control. Here it is. Select it and open. So I'll just give a description, that is open loop regulation of modulation signal. Alright, you can add anything you want, no problem. Save the control file, and now that we have this, let us configure the control. So in this configuration of control, let's start writing some code first. The first thing we need to do always is let's add a time event. So let's add a time event variable. Now time event variables, as I said before, are local to each and every control file, so you can have the same time event variable on all your control files, not a problem. So let's just do that, and initial time event is 0. Save it. So now that we have a time event, we can just come down and say if t clock is greater than equal to t1, this will be our control code, and of course we just have to increment it by some value dd. So now the question is, what will be a dd? When you are regulating your modulation signal, typically there are several strategies you can use. One strategy is you are going to change your duty ratio once in every carrier waveform. So in every sawtooth waveform, that is when it starts from 0 goes up to 1, in that one cycle you change it once, right? There's no need to change it more than once, just once. There are of course some other strategies where they change it once in every few cycles. So it may be once in 2 cycles, once in 5 cycles, so on and so forth. There may also be more strategies in which you may want to change it more than once in a cycle, but I personally can't think of anything, because once you set your modulation signal, you are deciding the width of your pulse. So typically you would not want to change it more than once in a carrier waveform. So that means dd should be equal to the switching frequency. So let's just put the switching frequency. Actually, we can copy this and we can just say 1 by switching frequency. So what we are saying is that 1 by switching frequency is the time period of this carrier waveform, right? Because when we set the switching frequency, we are setting the frequency of the carrier waveform. So this is once in a carrier waveform, or rather the carrier waveform time period. That's good enough. So now that we have this, we have now set our clock. So what we need to do next is we are now going to change the duty ratio. So that for that, let's create another static variable. Static variable would be, you can name it anything you want. Let's call it mod signal. You could also call it duty ratio, that's not a problem. And let's copy this and let's bring it here. So what we're going to do here, again, really speaking, you would need to implement a PI controller or some other form of controller. There are many other forms of controller. If you want to look at advanced controllers, there is deadbeat controller, there is pole shift controller, there is several others. Or you can even look at something like proportional resonant controller. It's a very vast topic, I won't talk about it. What I'm going to do here is I'm going to do a very simple concept of just incrementing the modulation signal from its existing value. So I'm ramping it up from 0 to some value, right? So let's say, for example, at every carrier waveform, we increment it by a small value. Right? Now, eventually, let's say we want to reach something like 0.3 or let's say 0.7. Let's look at 0.7. So which means if we want to increase from 0 to 0.7 by, let's say, in around 0.1 second, right? The rate at which you could increase would be around something like this. It doesn't really matter. You can play around with it. And of course, let's use the short form. We don't have to write it like this. It's a more elegant Pythonic way. So we are incrementing the modulation signal from its existing value by 0.01 at every carrier waveform time period, right? So it starts at 0 and increments. And the only thing we're going to say is if mod signal is greater than, let's say, 0.8, then mod signal is equal to 0.8, because you cannot increment your modulation signal beyond 0.1, or rather beyond 1. So I'll just put that as a comment. Mod signal, or rather modulation signal, cannot exceed 1, because that is your carrier waveform magnitude. Actually speaking, modulation signal should be slightly lower than the magnitude of the carrier waveform, so it should probably be saturated at around 0.98 or 0.99 or 0.97, something like that. But anyway, those are implementation details that don't really matter. We are just looking at the concept. So now we have created the modulation signal. What we have to do now, we have to now feed this modulation signal to the gate signal, to this file. So we are going to connect these two control files together. And for that, what we need is a variable storage element. So we have to add a variable storage. And here, it's always advisable when you have a variable storage to give the file name as a prefix and then the variable name. This is to ensure that you know where the particular variable storage, or rather the global variable, originates from, because if you do not include this and you have several control files, you could kind of lose track of what it is. Alright, so, or rather where it generates. So you could end up modifying it in different places and messing up your control. So that's why have this practice of prefixing the control file to any variable storage variable name. Alright, so now variable storage status, yeah, well, you could save it, not a problem. So let's store it and save this file. So now let's go back, copy this, go back to our code, and here I just have to equate it to the modulation signal. So all I'm doing is I'm saying I'm starting up the modulation signal from 0, ramping it up gradually, that is, I'm increasing it by 0.001 in every carrier waveform, checking if it is greater than 0.8. If not, I'm saturating it at 0.8. So if it is greater than 0.8, I do not let it exceed 0.8. You can of course change this to anything you want. And what this means is your modulation signal should gradually increase from 0. So let's go check it out. So now of course we need to use this in our gate signal. So for now what we were using is we were setting it, or rather actually I will not delete it. I will add another file, another variable, and let me comment this instead. So I'll comment this. So this is just to show that I have changed the way the modulation signal is generated. Before the modulation signal was constant, now it should gradually ramp up. So now that we've done this, let's go and run this file. So just a quick look, do we need anything else? We have a static variable, we have control inputs. Now realistically speaking, you would need a control input, because when you're doing any kind of control, you need of course to measure your system variable. So we need to measure the voltage, we need to measure the current. So you would at least need to measure the output voltage. You may also need to measure the inductor current. You may also need to measure the switch current, depending on how complex your control is. But you would at least need to measure the variable that is you're being regulated. So the variable that is being regulated is the output voltage. So you would need to measure that. This is an open loop control, so I'm not doing that, but you would have to do it if you need to implement it. So let's go back and run this simulation. So I'm going to click on the run button. As always, go to the command line and check if there is an error. There is no error, so we are okay. So now that we are okay, let's go and plot on something. So do we have a modulation signal anywhere? No, we don't. So the only thing we have is this one, right? So what we can do, we can create a plot and call this mod signal and plot just the modulation signal, right? Because we do have that. So we have open loop control signal, so we just call this mod. Save the waveform, click on done, and we should have it all the way at the bottom. So we just go and plot this. So let's go to the file browser. We should see it. And yes, it is. So this is a pretty good one. So you see, it starts at 0, gradually ramps up, it gets saturated at 0.8, and this occurs in around 0.08 seconds, right? Now, of course, I just played around with some values. You can of course change this, you can increase it, you can decrease it, you can do all kinds of control you want, no problem. But even in open loop control, that's always possible, not a problem. So let's now go and check out what our output voltage looks like. And you see this is the output voltage. Alright, so you see the output voltage gradually ramps up. So you see there is a bit of a glitch here, and that the reason for that is because of the nonlinear nature of this buck converter, and because at low modulation signals there will be some amount of discontinuous conduction mode. This is probably the switch between discontinuous conduction mode to continuous conduction mode. And finally there is a saturation when the modulation signal is constant and saturated at 0.8, right? So now let's go check out what the inductor current looks like. And this is the inductor current. So you see the inductor current is gradually increasing, and there is some parts which have to be investigated because they look different. But what's important to understand here, and this is largely because of the way this particular converter works, because of the capacitor increasing, and there is several transients that matter. I would invite you to investigate this. What is important to understand is the reason is there is no major spike in the inductor current. Before, if you do investigate, I would suggest you go back and run the simulation with a constant modulation index, and you will find that there is a huge spike in the inductor current. That spike in the inductor current has now disappeared. And the reason why the spike in the inductor current has disappeared is because of one simple reason. We are now gradually ramping up the modulation signal rather than having it constant, right? So when the capacitor voltage is 0, the modulation signal is also 0. So therefore the pulse width is very narrow when the capacitor voltage is narrow. This is the reason why there is no sudden inrush of current, right? The current gradually increases. Let's go and just zoom in a little and see what's going on between this in this period. So let's go 0.049 to 0.05. 049.05. and you see this is what happened. So really speaking, what we saw before was actually just a plotting inaccuracy. We had this feeling that the current was negative, and that's one of the reasons why I wanted to investigate. It's actually not negative. What is actually happening is this little spike here is when the diode turns off, right? This is when the diode turns off, and like I said, this is discontinuous conduction mode, right? Just check out what's happening. When the inductor current increases, that's when the switch is turned on. When the inductor current switch is turned off, the inductor current drops, and here it falls to 0, and this is when the diode turns off. And this little glitch here that you see is the reverse current when the diode turns off, because remember, the way the simulator works, and typically this is the way any simulator works, the diode will turn off when the current goes negative. Alright, so when this rate of change is pretty high, it is impossible to arrest it as soon as it becomes 0. There may be a little bit of a negative spike, and that's what this is. So this is not really a huge negative current like the way we saw before. This is just a case of these spikes appearing like as if there's a huge negative current. So this is exactly what we saw, and like I said, for low modulation signals you do have discontinuous conduction mode, and as the modulation signal increases, or rather the duty ratio increases, the pulse width increases, that's when we move into continuous conduction mode. So we can check that out too. So let's go and plot another range. I guess we can say 0.5, or rather I wouldn't want to go that far, 0.0, or rather 0.7, no, that's too much, 0.07, 0.071, okay, we should have something. Yes, we do. Well, you see it's getting a little narrow. Let's go and plot a little more. I guess I could just go to 0.1, 101. And you see this is still different. So this is, you see, this of course is also a question of how much my load is. I would need to decrease the load, I would need to increase the load, sorry, not decrease the load, I would need to increase the load to make sure that this modulation, or rather the operation moves continuously into the continuous conduction mode. So for that, of course, all you have to do is just go and change the resistance. You can just change, but those are not really necessary. Just to confirm, what is our load resistance? This is our load resistance, and you see the reason is because we have such a low value, we have such a large resistance, and that's the reason, because the load is so low, and because the load is so low, we are working in discontinuous conduction mode. So anyway, coming back to the topic, this is pretty much the end. So let me just stop the simulation. With this I would like to wind up this particular lecture series, not really the entire lecture series of DC-DC converters, but just that of buck converter. So in the next lecture I'll be starting with boost converters, but before I do that, I'll just tell you about one little thing which is also advisable to do. Once you are done with your particular simulation, or rather you have achieved a certain level, it is a good idea if you export all your parameters as CSV files. Alright, so because remember, now we have only two CSV files, or rather there's only one CSV file, which is the circuit schematic, the buck converter.csv, and we have two control files. These are Python files, right? Now, quite often you would want to share these simulation files with somebody else, and when you share these simulation files with somebody else, you need to provide them with the parameters as well. And that means it's always a good idea that you export the parameters. When you click on this button, export parameters, it will export all the simulation parameters in another Excel sheet called buck converter parameters.csv. So we just go over, so we just go over and you'll see this Excel sheet, or the spreadsheet rather, not an Excel sheet, a spreadsheet which is a CSV file, contains all the parameters of this buck converter. So when you want to share your files, you can now share all these, you can share the parameter file along with the circuit file, right? So let's go back, and there's also another thing which you can do. We can also back up our control. So go to configure control and export control. So when you do export control, along with the Python file, it will give you a descriptor file, that is an underscore desc.csv. And what that desc means is, this descriptor file contains the list of all the variables that you're using to configure, right? So when, as before with circuit files, you can upload it, or you can give it to somebody else, and that person can upload it and you can get the simulation without having to actually add all the values. So we have one more control file, so let's just go and do the same for that. You can just say export control. I don't think it happened. No, it didn't. I don't think I pressed it. Yeah, now it did. So now you see open loop control. So CSV also has a descriptor file, and this descriptor file is very small because we have only 3 variables. So what's important is, with this we have now all these files that you can share with somebody else, and you are collaborating with somebody else, right? So with this we have now completed the buck converter simulation. Of course, this is by no means the end. You are welcome to play around with it even more, change different values, or even better, just implement your own control. So if you are working in control, you can go ahead and implement a control for it. That will be a very, very challenging topic. So with this, I will be ending this lecture. If you have any doubts about what I did, feel free to post in the comments and I'll be happy to help you out, or just email me on pythonpowerelectronics.com. And of course, if you are interested, you can always register for this course, in which you learn how to simulate the entire, or rather use Python Power Electronics for simulating courses. This also has a slightly more detailed simulation for buck converter. It has an entire section. So with this, thank you so much, and I'll be seeing you soon, where I will start the next topic, which will be simulating a boost converter. So goodbye for now.